All right, go take your textbooks out, open to page 307. Have a little bit of a shorter class period today, so we'll move as quickly as we can. Page 307, questions 14 through 17. Questions you were answering. We're actually going to look more at this content in our next lesson. We'll go ahead and take a look at the homework now. Question number 14, list and describe the three principal rays. This is going to seem, and hopefully you realized as you did your homework reading, hey, this seems really familiar. And there's a reason we teach the two chapters together. What did you have for question 14? Audrey?
The parallel ray travels parallel to the principal axis and then refracts through the lens to the principal focal point. The central ray passes through the optical center of the lens without deviation on the far side. The focal ray approaches the lens through F prime and refracts through the lens parallel to the principal axis.
Very good. So it goes through that secondary focal point and then refracts parallel. Number 15, list the 5 cases of image formation by a converging lens, describing the image in each case. There's actually 6, but Michael, what did you have? 4 cases of image formation by a converging lens.
The first case is placed greater than twice the focal length away. It is real inverted and reduced. The second case is placed exactly twice the focal length away. It is real inverted and unmagnified. The third case is placed between the focal length and twice the focal length. It is real inverted and enlarged. The fourth case is at the focal point. There is no image. And the fifth case is before the focal point, and the image is virtual, upright, and magnified.
Good. And of course, had we gone with the 6th case, which was an infinite distance from the lens, your point image at the focal point. Again, all of that should have sounded a lot like concave mirror, but it's for a converging lens. Number 16, what kind of image is always formed by a diverging lens, Audrey?
The diverging lens, a reduced, upright, and virtual image is always formed.
Good. Reduced, upright, virtual images. And number 17, state the lens maker equation and identify each variable. Michael?
1 over f equals the quantity of n minus 1 times the quantity of 1 over r1 minus 1 over r2. F is the focal point, n is the
focal length.
Focal length, n is the refractive index, and r1 and r2 are radii of curvature.
Good, for the 2 surfaces of the lens. Excellent. All right, again, we'll get into all of that in our next lesson. We won't have time to get to that today with the shorter lesson today. Let's go to review some things we talked about in our last lesson, and our last couple of lessons, and then Kendall will try to catch you up on what you missed in the last one. If you get a chance, go back and watch that video. We did record some parts just for you. We said hi to you and stuff like that. Anyway, we talked about the ability of a transparent material, whether it be glass, even water would be considered transparent material, whatever. Transparent materials' resistance to the transmission of light rays. What's that term? 2 words. A transparent material's resistance to the transmission of light rays. Optical density. And practically speaking, I said we could think of optical density as the ability of a material to not stop light. That'd be opaque material. More plain English. Chloe, would you wait? What's hinder mean, Daddy? Real plain English for Chloe. Ability to slow it down. Slow down light. Ability of the material to slow down light. We said that as light slows down or speeds up, it will change direction or refract. That's the word. Good, it will bend, but refract is the word we're looking for. 2 directions light can refract. If light speeds up, it will refract away from the normal. If it slows down, it refracts in toward the normal. Does the angle of incidence equal the angle of refraction? No! Otherwise, there is no refraction. No, the angle of incidence doesn't equal the angle of refraction. Trick question, no. Rather, the angle of incidence and the angle of refraction are related based on the optical densities of the 2 media. Now, to quantify optical density, we would take the ratio of speed of light at its fastest, which would be through a vacuum, and compare it to the speed of light in whatever medium we're testing. That ratio kind of quantifies optical density, and it's a ratio that we call refractive index, or index of refraction. We'll represent the index of refraction class with the letter N. So we would say that the index of refraction of some medium equals the speed of light in a vacuum compared to the speed of light v in that particular medium. And this was the first equation that we had for this chapter. Now, the first law of refraction does talk about the angle of incidence and the angle of refraction, but they are not equal. Rather, this first law of refraction, this equation sometimes called, named after the Dutch physicist who discovered this relationship, Snell's law, right? Is, how did I finish out that equation? Do you remember, Audrey? Used this in the homework last night or over the weekend.
And then, no.
Michael?
N sub n. Yeah, n one side. And then n2 side.
All right, I'm guessing we did the homework on Friday, so we've had a few days to forget. That's okay. N1 times the sine of theta sub I equals N2 times the sine of theta sub R. Also, these students just took a slew of achievement tests. Did you do any COGAT tests today? Okay, so their brains are mildly tired, perhaps fatigued from thinking about stuff that they don't normally think, or thinking ways they don't normally think, like on the COGAT test. All right, so anyway, N1 times the sine of theta sub I equals N2 times the sine of theta sub R. So the angle of incidence, angle of refraction, the sines of those angles are related to the indices of refraction of the two media. And again, as we use Snell's law, we want to consider, okay, what medium is the light starting in, what medium is the light going into second of all, and relating those. So this was the second equation that we needed, and I'm not sure if that was in your notes from 2 days ago or if that was last lesson, so want to make sure we catch up with some things there. The second law of refraction was basically the incident angle, refracted angle, and the normal all lie in the same plane. That's still going to be true. So the plane stays consistent. We looked at some interesting refraction effects like mirages and how, you know, in a glass of water or a container of water, the bottom looks like it's in a different position than it really is, stuff like that. Then we talked about this, that as light is in a high density medium, and if it tries to escape into a low density medium, what's going to happen to the speed of light going from high density to low density? What's going to happen to the speed of light? It's going to speed up. And that means the light is going to bend in which direction? Away from the normal. So as the light bends away from the normal, it's going to refract further and further away, the greater and greater the incident angle becomes, until eventually you could get the light refracting 90 degrees away from the normal, meaning the light no longer really passes into that second medium. It now is trapped in the first. What do we call the incident angle that produces a 90-degree angle of refraction? The critical angle. We're going to look at that here in just a little bit. So the critical angle is the incident angle required to produce a 90-degree angle of refraction. Any incident angle greater than the critical angle will not produce refraction at all. Rather, we get a phenomenon called total internal reflection. What is that, class? Total internal reflection. We'll be looking at total internal reflection quite a bit today as well. Your homework was to practice with Snell's law, and then that critical angle. We said it produces a 90-degree angle of refraction, correct? And we said that the sine of 90 degrees, U2, is always 1. So in a sense then, if you have a critical angle, this is gone. You're really just left with N1 sine theta sub C equals N2, or we said the sine of the critical angle equals N2, and then divide away the N1. And this was the third equation. This is the second equation we looked at in our last lesson, but our third equation from chapter 22. Turn over the page then to page 308. Let's take a look at problem number 5. Read that problem for us if you would, Audrey.
Light incident on a boundary at an angle of 31.4 degrees is refracted at an angle of 45.2 degrees. If the second medium is air, what is the index of refraction for the first medium?
Okay, so light starts out in some medium that we do not know, and it goes into air. Well, we know air's refractive index. It's on that table of refractive indices. I believe it's back on page 294, though you two may have it memorized by now from using it so much in the last lesson. What is air's refractive index?
1.0.
Yeah, there's 3 zeros in there before the 3. And it says that the light is refracted at what angle, Audrey?
31.4.
It's refracted at what angle?
45.2.
45.2 degrees. It is incident at what angle?
31.4.
31.4 degrees, and the question is, what is the index of refraction for this first medium of unknown identity? Well, it makes sense, does it not? I mean, other than a vacuum, which there's not that big of a difference between the speed of light in a vacuum and speed of light through air, it's very similar. It is understandable then light should travel fastest through air, slower through some other medium, correct? So therefore we should have a greater angle of refraction from light speeding up and bending away from the normal, and a smaller incident angle. To solve, we'll plug this into the calculator. Kendall will do this with us. We'll start by taking I would start by taking the sine of 45.2, so 45.2 sine. You'll get that decimal 0.7095. Multiply the sine of 45.2 times 1.0003. And you've got, again, you're barely multiplying by anything other than 1, so the number on the calculator looks very similar, slightly different. Then we need to divide away the sine of 31.4. So we'll hit divided by 31.4 sine equals. Don't forget the equals at the end. What do we get for that refractive index, Audrey?
1.36.
Good, rounded to 3 sig figs, we'll get 1.36. Remember, index of refraction is unitless. Meters per second in both cases will cancel. So we just get 1.36. Did you get that for your answer? And if we were to flip back to page 294, it looks like this may be ethanol. That doesn't mean it is, but ethanol happens to have a refractive index of 1.36, so it's possible that we've got that substance there. Questions on how to use Snell's law? All right, and in this case, what we did to use it, Kendall, was we were finding an index of refraction. I believe problem number 6 varies just a little bit. It does. Michael, read it for us.
Light at 589 nanometers emerges from water into the air. If the angle of incidence is 22 degrees, what is the angle of refraction?
All right, so here the 589 nanometers, again, is just saying yellow light. We don't really care about the wavelength per se, but it goes from water, class, into air. So the first substance being water means we know the refractive index. We can look that up on the table on page 294. What is that refractive index, Michael? 1.33. And that refractive index needs to be multiplied by the sine of the incident angle. Do they give us the incident angle?
Yes.
Yes, it's
22 degrees.
22 degrees. Notice we're going with 2 sig figs now. We know that air is the second medium. We know air has a refractive index of. And we want to find this angle of refraction. Well, when you're finding an angle, Kendall, that means we need to get the theta sub r by itself. Well, let's start by multiplying on this side. Start by taking the, to get an initial decimal of, good, we multiply that by,
1.33.
and then we're going to need to do what next? Divide away that 1.0003. Again, we're going to have a very similar number to what we just had. Now, what we've got on the calculator, Kendall, this weird decimal, is the sine of theta sub r. I don't want the sine of theta sub r. I just want the refracted angle. I need to get rid of the sine. How do we get rid of sine? Arc sine. It's that second function sine. So take the second function sine on the calculator, and it'll give you the refracted angle to be 29.87, but we are only using 2 sig figs this time, so we'll round to say 30 degrees. Did we get a 30 degree angle of refraction? And Kevin, you would do the same if you were finding the incident angle. That arc sine is how you would get rid of the sine. Anytime you find an angle, if you were finding the index of refraction, then you know both angles, you just take the sine of them. Questions on that? And again, you'll see that if you go back and watch that lesson from Friday. Drop down to problem number 8, if you would, and read problem 8, Audrey.
Assuming that air is the second medium, calculate the critical angle of refraction for plastic with a refractive index of 1.48.
Good. Now again, to be clear, it says critical angle of refraction. It's meaning the critical angle dealing with the refraction with plastic. It's not saying the critical angle is the incident angle, for the record. Just clarifying the book's statement there. So it says, assuming air is the second medium, and there's a plastic that is the first medium, find the critical angle. Well, we need to take air's index of refraction, class. And it says this particular plastic has an index of refraction of 1.48. And then we simply need to divide those two indices of refraction. But again, Kendall, that gives me the sine of the critical angle. So to get just the critical angle, I'll take the arc sine, that inverse sine, if you will. So on the calculator, we'll punch in the ratio first, take the arc sine of it, and what is the critical angle for light trying to go from this particular plastic into air? Kendall?
42.52.
Good. 42.52 looks like 3 sig figs, so we'll say 42.5 degrees is our critical angle. Did you two get that answer? All right, questions on that math. Very similar to the other, just with the refracted angle taken out. Look at problem number 9. And you're going to need a reference, page 294 for this. Find the critical angle of light traveling from flint glass into ethanol. From flint glass into ethanol. Now just find that critical angle. What's the equation we're using here, class? Sine of theta sub c equals n2 over n1. Now, Kendall, I pointed this out to the class on Friday in the video, but if we were to accidentally get these mixed up, we were to accidentally put the first medium over the second medium, your calculator will say error. That means you goofed. Flip it the other way and now take the arc sine. So it's kind of got a built-in safety feature, so to speak. The second medium, class, is ethanol. So we need to start by taking ethanol's index of refraction, which is the 1.36 we saw earlier, divide that by the first medium, the flint glass index of refraction, which was, and then take the arc sine of that to get the critical angle. What is the critical angle here? 55.01, I guess 3 sig figs, 55.0 degrees. Did we get that answer? Again, if you plugged it in the other way, the calculator would just say error, and you'd rework it. Look at problem number 10 now. Read this problem for us, Kendall.
Green light passes from film to quartz. What is the angle of incidence when this light is refracted at an angle of 26.2 degrees? What is the critical angle for this light passing from the diamond to the quartz?
All right, so there's two parts. The first part, they give you the angle of refraction. They want the angle of incidence. That's Snell's law. The second part, they want the critical angle. That's this one. So you're going to practice with both of these equations now as you do problem number 10. Take just a few moments to work that. And the light is going from diamond into quartz. We do this demonstration in class. If one of you has a really big diamond, anyone? Just leave it with me. I'll do the demonstration in a year or two. After you've forgotten about it. Just kidding. for the first part of the problem, did we set it up this way? Diamond being the first medium, so the 2.42 times the sine of theta I equals quartz being the second medium, 1.46 times the sine of that refracted 26.2 degree angle. You plug it in that way.
How do you swap the sign?
You put the 26.2 here. Careful. Okay, so that's where you got to read carefully. It says it's refracted at 26.2, and it says what is the angle of incidence. So read carefully so you know where to place the angle. All right, so Audrey, go and redo it with me here. We'll go ahead and start on this side, the 1.46 times the sine of the 26.2. Divide out the 2.42. And then finish by taking the arc sine. And Audrey, what should we have for the incident angle here?
15.4 degrees.
Good, rounded 15.4 degrees. Did you two have that? And of course you've got that now. All right, so again, angle at 15.4 degrees from the normal refracts all the way up to 26.2 degrees because it's able to speed up going into this less optically dense medium. Well, the next question is, okay, at what incident angle would we get that 90-degree refraction? What is the critical angle? So for this, we're going to take the formula, sine of theta sub c equals the n2 over n1. Nice thing is we've already got these two things here. So we're going to take the second medium divided by the first, take the arc sine, and what incident angle would you need? How far from the normal would the first angle have to be to refract along the surface? Class? Good, 37.1 degrees. That's your critical angle. Questions on that? All right. Look in your books then, if you would, at page 298. 298. I want to briefly talk about some different things here with critical angle. One of the things kind of interesting is that direction reversal in a prism with a laser beam. How and there's sensors, by the way, that are used like garage door openers. How many have ever noticed if you run past the sensor, the garage door's on its way down and go back up? Anyone ever play with that and see if you can jump over, step over? Anyway, the idea there is there's a beam of light, electromagnetic wave, if you will, that light will be redirected and back to the original sensor. If that beam gets broken, of course they have sci-fi movies with that as well. But again, the sensor needs to pick up the beam. So some of that is used there. I really want to point out the diamond, though, because we talk about diamonds have this certain amount of sparkle, a certain amount of fire to them. And the key with the diamond is that high refractive index. See, if I just had a piece of glass and light shines down on it, the light goes right through the piece of glass undisturbed. But with a diamond, the facets are made in such a way that you want a very large, flat surface, the bigger the better, because it looks cool, right? Nice big surface of the diamond at the top for as much light as possible to enter. But the bottom of the diamond is angled. And the idea is to angle it as steeply as possible. A shallow diamond is not much better than having a flat bottom here. So light could go in, light goes straight in here. Well, let me blow this up a little bit bigger here. There's the bottom of the diamond, okay? So here's diamond. Light comes straight down through, it hits here. Well, with respect to the normal, what's this incident angle? Right, the idea is that if you angle the bottom shallow, you have a very small incident angle, don't you? The deeper you can make the diamond, the bigger this angle tends to be. Well, what that's going to do is it's going to trap the light beam. It's not going to be able to refract out. Total internal reflection is going to take place, and it's going to reflect over here. The idea is to get that light to then come back out, or perhaps hit the faceted edge, come back over here, bounce around a few times before coming out. A diamond has the unique ability to trap light the longest because, as we are going to see here in just a moment, from a diamond going into air, you actually don't need a huge critical angle. What would be, let's see, diamond we said is 2.42, right? And air is 1.0003. What is that critical angle at your seats? Oh, air, excuse me. Air is the second medium. I got the error message. I told you, it catches itself. I did that as an illustration. 1.0003 divided by 2.42. There we go. What is that critical angle?
88.59.
Did you take the arc sine? I got 24.4 degrees. Try it again, Audrey. 24.4 degree critical angle. So 1.0003 divided by the 2.42, and then take the arc sine of that. Insert there.
Yeah. Okay.
You got it now. Okay. 24.4 degrees is all you need to get that light to stay in. And of course, every time it reflects off, it has a little bit of the prismatic effect where the light disperses just a little into the colors of the spectrum. And every reflection is going to disperse just a little bit more to where it comes out the top. You've got all those colors in radiant beauty. And again, the more light rays you have coming down, they're all bouncing around inside, hitting off the facets. The other thing they'll do is, this is kind of a side view, but if you were to turn it, you get a lot of individual cuts in the diamond, as many facets as possible. And they call this the cut of the diamond. And so one day when you find that woman of your dreams, you say, this is the one. I want her to be my woman for the rest of my life. Okay, just don't call her a woman or the rest of your life will be short. And anyway, and you go to buy that diamond, there's all kinds of different things, color, inclusions, clarity, and cut is one of them. And so the ideal cut is what they used to call it. They've changed the name and actually forget what it's called now. Radiant cut, maybe? Anyway, when I was buying the diamond for my wife, it was the ideal cut. And so it's not a big diamond, because I'm a high school teacher, I don't make a lot of money, so it's not a big diamond, but oh, is it beautiful. And the light really reflects around nicely, because they made a lot of those little cuts at the bottom. They set the cut deeper to give it really good fire and brilliance. So anyway, all those things you get to think about when you're looking for the perfect diamond that you can afford. And then, you know, it's funny, and you tell what your budget is, and they laugh at you. Anyway, anyway, I digress. So anyway, that's something I thought was interesting there with the diamond. Look at the next page, page 299. Of course, this is one of those invisibility ideas. Of course, we looked at the Instaglass thing. Okay, to give you the same index of refraction, if you will, as the background, or, you know, paint yourself to match. But in theory, we talked about fiber optics and total internal reflection, right? Light goes in, it gets trapped, it circulates around. The thought is, well, what if I could redirect light from this chalkboard? If I wore a suit of some kind of fiber optic material so that light from right behind me refracted around my body, was trapped around my body, and then somehow we could cause it to refract back out this way, to where you could literally see right through me. Invisibility cloak, so to speak. You could see what's on the other side of me as if I were not there. And so, obviously, there's difficulty, of course, in getting, you know, trapping the material is one thing. Fiber optics do a great job of trapping, but then how do you redirect so it goes to all viewers from all angles? And then the other thing is, while light is refracting, or, you know, totally internally reflecting, it slows it down. So you would, at the very least, if it were possible with this technology, right, as I walk past the chalkboard, you'd see like a delayed action, right? You'd see a little bit of a blur, like you'd see it, and then it'd be a little weird, so it wouldn't be a perfect thing, but that's one of the concepts of the invisibility cloak, so to speak, that scientists are toying with, because let's be honest, wouldn't that be cool, right? Can you imagine in combat how handy that would be? And of course, spy movies, you know, they have that kind of thing. And anyway, just cool stuff that you could theoretically do. But that's one of the things they're kind of thinking, okay, how could we make this happen? And this idea of total internal reflection is one of those things. We're going to do some work here in the little bit of time we have left to demonstrate total internal reflection. If you're watching on YouTube, it's not going to be quite as cool as being able to see it in the classroom. There's some things that you don't see on the videos the same way. But anyway, a couple of videos for you to watch in the description. If you will watch those, your homework is also in the description of the video. It is simply a handout for you to complete this evening.